Okay, even I can do the calculation. So very simple. So that's 100, this is 20. This is 20 for glass fiber, 100 for carbon fiber. Just plug in the numbers in this simple expression. So you get E sub C, which is the modulus of the composite, works out to be for different volume fractions. For 10% volume fraction, we use VF equals 0.1, and then we get the corresponding ratio, which is 2.9. So EC over EM is 2.9 for a volume fraction of 10% for glass fiber. So EC would be 2.9 times EM is 0.5 MSI, which is nothing but 3.447 GPa. So 2.9 times 3.447, that's 10 GPa. So calculation is very simple, right? So other 5 numbers, you can get it yourself. It's very simple. Any questions? No questions? Okay. So I'll move on. So same thing with carbon epoxy system. Our ratio is 100 here. 100 minus 1 is 99 times plug in your VF 10%, which is 0.1, and you get your corresponding E sub C. So let's go back one slide. Try to remember. Some of you have very good memory, so I will ask you for these numbers. So let's work with either one is fine. Let's say 37.58 for carbon. Okay, 37.58. Remember that, or write down somewhere. For a VF of 10%, carbon epoxy system, 37.58. For 45% volume fraction, carbon fiber with epoxy, 157.5 GPa. Let's say 157. What about VF of 75%? It's close to 260 GPa. 75% carbon fiber. Go back. If I go back, you will see glass epoxy fiber, 10%, this is 2.9, as opposed to 37.58, right? My memory is not that good. I'm cheating. I have two slides here. If you see, I have 2 slides here. So I'm cheating. I'm just reading from here. But anyway, it's 37.58. My memory is so bad. I meet somebody, let's say, take a name, Gopal. I'll turn around, I'll say Venugopal or something like that. So my memory is very bad, very bad. So if I do that to you, don't mind. That's normal to me. So anyway, so coming back to this, you see this is 2.9 with glass fiber. This ratio matters. This ratio is very important. That's what matters. That ratio is 20. For a ratio of 20, I have 2.9 how much was it? 10 GPa. Whereas if the ratio is 100, that value is 37.58. Big difference. Okay? Same thing for 45%. For 45%, 32.96 is what we got. And in this case, I have 157. Where is 32.96? Where is 130 or 157? That's almost a ratio, or almost a 5 times, almost 4.5 times. Okay? And for 75%, we have 260, and this is 52. 52 here, 260, more than 5 times. So that's what matters. That's what I keep on telling. If you want to improve your composite material, what I need is larger stiffness. If you give me larger EF, you will sell more. That's my so-called mantra to all my sponsors. Okay, now we'll talk about some actual stress strain curves. Okay, now we just peripherally looked at the numbers. Now we'll look at the stress strain curve. Remember, one of you did mention this. I said, what do you remember from yesterday? One of you said linear stress strain curve. Excellent answer. This is exactly what it is. Matrix is likely, some matrices will have linear stress strain curve. Linear stress strain curve. All fibers, without any exception, will have linear stress strain curve all the way to failure. Okay, and this yellow line is symbolically, it's not exact, but this is symbolically some stress strain curve for a matrix. This red line is stress strain curve symbolically, it's not drawn to scale, of a fiber. Okay, so our composite can have depending on the amount of fiber volume fraction you have, depending on that you can have E value or the slope of the stress strain curve, theoretically speaking, can be anywhere between here and here, right? Nothing outside. Either it will be a minimum of this or a maximum of this. All right? So that's how you have to look at your composite properties. If you got some other value more than the fiber modulus, that's not right. There's something wrong. Okay? If you're calculating, that's how you check your work. So that's for a linear system. For most matrices, you will have some nonlinearity, a little bit of nonlinearity after a certain time. So it will be linear up to some point, and then beyond that it will be slightly nonlinear. Okay? In that case, the stress strain curve for the composite will fall somewhere between this straight line and the stress strain curve for the matrix. It cannot, again, I repeat this, it cannot fall outside of these two lines. Okay, it has to be confined between those two lines. Makes sense? Now we'll talk about load sharing. So if you apply just let's say unit load, some of the load is carried by the fiber, the remaining is carried by the matrix. Just wild guess, which item would carry the most load? Fiber, obvious, right? Very clear. So clearly the fiber will carry the most of the load, but matrix also is likely to carry some amount of load. Okay, so for load sharing we'll use the same simple mechanics equations. Stress equals or strain equals sigma over modulus. So that's what we have here. I will not go over all the lines because it's useless. You all know this so well. You teach all this stuff, so you really don't need me to remind you this. But so finally you'll see when I rearrange these terms, you will see PF over PC will work out to be this equation here. PF over PC equals EF over EM over EM plus VM over VF. So if I know, I don't have to know EM. However, if I know the ratio, that's good enough for me. And the ratios are generally, we know what they are. If I'm using glass, it will be around 20, 22, something like that, or 18. Okay, so an average value of 20 is reasonable. If I'm using carbon, it's about 100 or 90 or 105. So the range is known. So before you do actual calculation, if you are starting from scratch, all that you need to know is what type of fiber you are going to use and what's the ratio of EF to EM. So if you know that, and then you have something in target, something in your mind, okay, you say I want to use VF of 30%. Last time it worked with 25, this time I want to use 30%. So VF is also known, 0.3. Okay? So VM is obviously, if VF is 0.3, VM is 0.7, right? 1 minus 0.3 is 0.7. So with only that much information, you can find out what would be the load carried by fiber compared to the entire composite load. Does it make sense? So it's as simple as that. So we already mentioned that. We'll move on. So if you see the variation of the load carried by the fiber to load carried by the composite, so you will get this kind of curves. So on the x-axis what I have here on the x-axis, this is again from one of the books, from Barbito book. So on this axis, x-axis, I have 0.2, 0.4, 0.6, 0.8, that's fiber volume fraction. That's on the x-axis. What about on the y-axis? On the y-axis, I have PF over PC in percent. PF is the force carried by the fiber. PC is the total force. So PF over PC in percent is on the y-axis. I have 20%, 40%, 60%, 80 and 100%. So we also have some numbers here. Okay, if my EF over EM is 1, EF over EM equals 1. So when do you get EF over EM equals 1? Same material. If you are using the same material or material with same properties, EF over EM equals 1. EF, that's the modulus, not the volume fraction, but modulus. That's equal to 1. In which case you have a linear relationship. Of course, if I extend this to 100%, this line will pass through that point. Okay? But we are only showing it up to 80%, 0.8. EF over EM, we talked about EF over EM of 20. So in case of 20, you will see the variation is non-linear. It's not straight line, but it's non-linear. If you have EF over EM of 100, what you can see from this is, even if you use a fiber volume fraction of 0.1, which is 10%, which is small amount, right? Very small amount of fiber, if you have very large modulus, very large modulus of elasticity of fiber compared to the matrix, most of the load is carried by the fiber. That means it's an efficient composite, right? Your material is fully being utilized. Does it make sense? So you want to maximize, once again, maximize the modulus of elasticity of the fiber to get most out of your material. Okay? That's the significance of this figure. So once again, I have a few numbers here, and these numbers are based on same carbon fiber, 50 MSI, glass fiber of 10 MSI. The ratio of fiber to matrix modulus values is 10 over 0.5 is 20, and then the ratio of EF to EM for carbon fiber is 100. With those numbers and with fiber volume fraction of 0.1, that is 10%, okay, you will see PF over PC is 69% just with 10% fiber volume fraction, even for glass. That's where the advantage is. Okay, that's the advantage. So even for glass, 69% of the load is carried by the fiber. What about for 10% of volume fraction? If it is 45% volume fraction, you can get as much as 94. What if you use, say, 75%? You really don't even have to use 75%. You know why? Because even with 45% volume fraction, I'm able to achieve 94% load transfer. So why do I need 75%? It's not efficient. You're using too much material without much gain out of it. Okay? Same thing with carbon fiber. Carbon fiber has a larger ratio of EF to EM, which is 100. So if I plug in those numbers, even for 10%, just 10% of fiber, I'm able to carry 92% of the load. So why do I even want to go to 45%? I don't have to. You see the difference? That's, if you understand this really well, you can actually design your composite or even your reinforcing bar without using too much material, which will go to waste. Even if you add more material, doesn't mean you can, it will give you any more benefit. Okay. So Now I will introduce you to a concept which is similar to what we use in our steel reinforced concrete. Okay. So, just before we switch to that, does anyone remember why? Of course, you all remember, but does anyone want to say why we use minimum area of steel in steel reinforced concrete? What's the purpose of minimum reinforcement? One at a time. Shrinkage crack is one. That's for beams. I'm talking about flexure members. Shrinkage cracks and distribution steel are mainly for crack control, but normally they are transfers to the longitudinal direction of the member, right? So in beams we don't provide transverse reinforcement. My question is why or what's the basis for the minimum reinforcement equation in your beam design?
Only for columns we have. If beams we don't have. Only for columns we have minimum maximum reinforcement. For beams there is no condition.
I don't know about that. You should have it. I am sure you have it. I'm absolutely sure. I think. Under reinforced is something else, because under reinforced is when you are forcing your steel reinforcement to reach Fy. That's under reinforced, right? But we don't actually provide. Okay, we provide if your steel area from your design calculations works out to be very, very small area, you still need to provide some amount of steel. And my question is, why? No, don't, no, that's
providing minimum tensile strength for the concrete, that much minimum steel is required.
I think you are going in the right direction, but I'll explain it,
So for
rephrase
example,
it.
if we are providing a 0.12% of PD, so it means minimum that is required for providing tensile strength for that section.
Okay, all right. Any other thought? That's a good one. You are going in the right direction. Any other way to explain it?
Control the strain of the material, whereas without providing the minimum steel, it will undergo some brittle failure.
Yes, that's the second part I agree. First part I don't. Second part is correct. So the reason you provide minimum reinforcement is if you have a plain concrete specimen, you apply a load, it will fail at a certain point where it's also called modulus of rupture, when the stress at the bottommost bottommost fiber is equal to the flexural tensile strength of concrete, it will become two pieces. No reinforcement becomes two pieces, right? So the code tells you don't let that happen. If you provide very small amount of reinforcement, it will become two pieces if the area of steel is less than the minimum. The minimum area is based on the fact that whatever moment strength can be achieved by plain concrete specimens without any reinforcement is the same amount of moment of resistance with reinforcement for a cracked section. Does it make sense? One is uncracked section. That's where you use flexural tensile strength, which is also known as modulus of rupture, right? So if you don't provide any steel reinforcement, you apply a load, it will crack. It will act like an uncracked section all the way to failure, and it will become two pieces, right? So let's say that's 10 kilonewtons. I'm just giving you a number, throwing out a number. It may not be 10, it may be something else. 10 kilonewtons, okay? Now you design a beam considering cracked section with reinforcement. That strength should correspond to a load of 10 kilonewtons. That's the basis for minimum reinforcement. Therefore, if you have minimum reinforcement, it will not allow the concrete to fail in a brittle manner like a plain concrete beam. Okay? Anyway, similar to that, we have for composites, we have a minimum amount of reinforcement or fiber needed to prevent brittle failure of matrix. There is also a critical critical volume fraction for composites. So any fiber you add to the composite will actually give you some benefit. So two different things. You have, one is you want the composite to have some benefit by adding the fiber. Otherwise, what's the point of even providing the fiber, right? Just like in reinforced concrete. What's the point of providing steel reinforcement if the load is so small that even without any reinforcement it can work? That's unlikely, but that's the concept. The other one is any amount of fiber you add beyond that critical point, that's where you actually see the benefit of fiber for the composite. I don't know if I explained it clearly enough for you to understand. So there are two different fractions, large volume fraction, small volume fraction. Those are little bit misleading terms, but large and small are very, very small. Both are very small percentages. I'll talk about it in a minute. So if you have VF above a certain amount of VF minimum, so that's our basis, VF minimum. In that case, the matrix will not be able to support the entire load when the fibers fail. Because whatever is the load carried by the fibers will be transferred to the matrix, but if the matrix is not capable of carrying that load, it will fail, right? It's brittle failure, just like our concrete. That's the basis for our minimum reinforcement. So it will not be able to support the entire load when the fibers break and they fail in a sudden manner, all of a sudden without any warning. Tensile strength of the composite is assumed to be equal to, let's say, a stress corresponding to epsilon F star. What is epsilon F star? Epsilon F star is the strain of the composite at failure. Strain of the composite at failure. So the stress in matrix, I'll show you a couple of figures, then that will clarify stuff better. But the stress corresponding to the